As I said, my name is Jane Kelly, and I manage a program called the University Partnership Program, or UPP. And the IEEE Texas A&M University Student Branch is part of the UPP. And I know you guys have heard it a lot today, but I just feel like a proud auntie, so I just want to point out, remind that the student branch came up with this just a little over 3 months ago. So it's pretty remarkable that in this short time they were able to pull off this magnitude of benefits. Congratulations. So I'm going to talk a little bit about IEEE and how to get involved with IEEE beyond today. So IEEE is the world's largest technical professional organization with 486,000 members around the world. So we're a quite large organization. A lot of times students think of IEEE and they think of it as a club on campus, but IEEE is much broader than that. As you heard some today when IEEE USA was talking, for example. But the key to getting the most out of being within IEEE is to find your community. And there are a lot of opportunities within IEEE to become part of a community, to attend conferences, to volunteer. There are so many ways to get involved. I often tell students it's not a lack of opportunities, sometimes it's an overwhelming amount of opportunities and really finding your niche. So when we talk about IEEE is actually organized a couple of different ways. One is geographically. So IEEE is a large international organization, but within IEEE there are regions, and as you've heard today, we're part of IEEE Region 5 here. And then within the regions, there are local sections. And so anyone at Texas A&M, for example, is part of the IEEE Houston section. But I know we also have students in the room who are part of the IEEE Lone Star section, the IEEE Central Texas section. There's another, but I just don't like it. But yeah, a couple of different, IEEE Dallas and Fort Worth sections. I think that's the from them as well. So those local sections provide you the opportunity to attend local programming and create meaningful relationships within your local community, right? And then, of course, you have the IEEE student branches. And so hopefully all of you are involved with your IEEE student branch, but if you're not, please go back after today and find your IEEE student branch and attend the next meeting that they're having. Because that's the best way to start as a student, is to get involved with the IEEE student branch level. Now, in addition, IEEE is organized by societies. So IEEE has 39 technical societies that cover a wide range of technical interests. So, for example, the IEEE Power and Energy Society is IEEE's oldest society. The IEEE Computer Society is our largest society. The IEEE society that a lot of people are involved with who work in the semiconductor field, for example, is the IEEE Solid State Circuit Society. That's one of the societies they participate in. So really, you can see here that as you get out into the workforce, finding that technical society will be really important, because that's where you're going to get the more targeted research, the more targeted programming work, targeted professional development, and to actually network with people in your industry. But we don't just have technical societies, we also have technical communities, technical councils, special interest groups, and affinity groups. So you might be interested in participating in IEEE Young Professionals, or IEEE Women in Engineering, or Tech Ethics, or IEEE Entrepreneurship, right? So there are things that are both technical and non-technical that you can get involved in within IEEE. And within a lot of your local sections, they're going to have local chapters of the societies or these affinity groups that you can get involved in. Another way to get involved with IEEE is through the Standards Association. So a lot of people only know IEEE as a standards body. IEEE develops standards that underpin many of today's top technologies. Probably our most famous is the 802.11 Wi-Fi standard, because people have seen that. It's on your devices, right? Somewhere that your device is accredited to that. But really, IEEE develops standards across all areas of technology. We currently have over 50 in the works on artificial intelligence. And they're not just technical standards related to artificial intelligence, they're standards related to the ethical implications of technology. How to safeguard children in the age of AI. opportunity because standards are actually developed in an open process. So you can walk into the standards development working group and actually sit in and participate as a member of the public. And it's a great place to network because think about it, if there are standards that are really important to a particular industry, all of the companies are going to assign people from that industry to participate in that standard. Because basically once that standard is defined, all those companies are going to agree to abide by it so that they have interoperable technology that works together. There's other ways to get involved too. You can see there's an SA open source community and there's an industry connections program. And so you guys have started out great by attending this event today, but where do you go next? So maybe you want to look into some of the IEEE technical conferences. So there's over 2,000 technical conferences around the world every year. And by technical conference designation, I'm talking about conferences where people have submitted their research and then their peers review it and select them to come to the conference and present that research. And so IEEE, like I said, has over 2,000. They're on every topic you can imagine. And it's a really great place to come to network, to learn something new, to walk the exhibit halls and see what companies are exhibiting. And here's just a couple of examples that are coming up in Texas over the next few months. And you can see it covers a wide range of topics. We've got biomedical engineering and electric machines and drives in Houston. Then Dallas is going to have a couple conferences on thermomechanical and electronic components. Then we can go down to South Padre for electrical insulation and College Station here. So here in June and July, there is a international conference on ubiquitous robots. So if you're interested in robotics, people from all over the world are going to be coming to present their research here in College Station on that topic. Another thing that's important for students is to be sure to check out opportunities to find an IEEE mentor. An IEEE mentor can help you in multiple different ways. They can help you, one, navigate IEEE to find that particular community that you want to be involved in. They can also help you navigate into the work field. We have IEEE mentoring program through CollabTech. Some societies have them. Some of your regions and sections have them. Some conferences have them. And even conferences that don't, it's just a great opportunity to go out and organically meet a mentor. IEEE also has exciting contests. I would encourage you to take a look at different contests because that is something you can participate in that helps you improve your skills. And it's a nice project that you can highlight on your resume. There are funding opportunities for students. So we have fellowships, scholarships, travel grants, and I'm just going to highlight two where the applications are open as of today. So IEEE Solid State Circuits Society has a coded ship travel grant award that's open right now. It's due on April 23rd, so it's a short time frame now. But if you win, you get a travel grant to attend VLSI 2025, which is a conference that's going to be held in Japan this year. Also, the IEEE Power and Energy Society gives out many undergraduate scholarships, and for the first time this year, they've opened it up to include any degree that falls under any IEEE field of interest. So you don't have to be just going to school for power. You can apply for this if you're interested in any area. And the application process closes April 30th, so it's coming to a close pretty quick. If you're interested in humanitarian efforts, IEEE has a ton of opportunities for that as well. Our tagline is advancing technology for the benefit of humanity. And just highlighting two quick things that are open right now is ethics in IEEE. So this is engineering projects and community service. They have a spring call for projects. You can get up to $10,000 in funding. So if there's something you want to do to work on that's an engineering related project that will improve your community or another community, this is a great opportunity. And then also right now through May 16th, the IEEE Connecting the Unconnected Challenge is going on. So this is a competition to help bridge the digital divide that you can think about. So those are just, I'm telling you, this is just a sliver of the kinds of things that are going on These are ones that happen to be open right at this moment. But that's why I talk about it. It's kind of broad. It's hard to find. It's, really difficult to navigate. So find that IEEE mentor, that IEEE staff member who can help you navigate and find your place within IEEE, including information on how to stay technically current. We've heard today that you're going to have to be a lifelong learner. And then I want to make sure I have time for a quick question in case anyone has one. But just a quick wrap up is IEEE can help you stand out through networking opportunities, through volunteering. Being on your IEEE student branch looks really good on your resume. It also gives you excellent soft skills and development of those leadership skills. You can participate in competitions or scholarships. All of those are marks of distinction that you can talk about and put on your resume as well. And if you know the standards core to your industry, when you go into an interview, you're going to look really smart compared to a lot of students. A lot of people are not familiar with what standards are important in their industry. All right, so questions.
Anybody?
Sure.
I'm not going to introduce myself because that'll give away my question, but if I want to get more involved in IEEE student activities in Region 5, where would I go?
I believe you go to Miss Colleen Bailey right here. So Colleen is the Region 5 Student Activities Chair. Each region has a SAC, is what they call them, and everything in IEEE's acronyms. There's usually a student representative as well for each region. And they're a great resource to help you if you're currently an IEEE student branch leader and you don't know what to do or how to start, reach out. There's resources, there's people we can connect you with, there's people who know what they're doing. So connect with me on LinkedIn if you want help trying to find your place within IEEE, and I will be happy to sort of guide you to that. Any other questions? Yes, we have one question here.
Hello. I was wondering, for the IEEE scholarships, do we have to be a member of IEEE in order to apply?
Yes, you will need to be an IEEE member. So it's $32 a year for students, but on top of that, if it's for a specific society, it depends on who's issuing or giving out the scholarship, you also need to be a member of that society or that organization. So Women in Engineering, for example, has scholarships, so somebody who wanted to apply for that would also need to be a member of the Women in Engineering. Great. Yes?
Oh, Gary.
Oh, mechatronics.
Yeah, I'm a mechatronics engineer, engineering student here at Texas A&M, and I was curious, what are the benefits to joining a particular society that kind of sparks your interest? Like, for example, me joining a robotics society, the robotics one show there.
Right, so once you're doing like a particular society, like the Robotics and Automation Society or RAS, you will start to be invited to specific programming and events for RAS members only, right? So they will have local, they might have a local chapter depending on where you live, and they'll have local things. You also get discounts to conferences, you get access to specific content, so maybe every society is different, so one society might give you their magazine and their main conference, so you get full text access to that content. Online, it kind of depends, but each society has sort of their own membership benefits, but they all have some particular benefits. So across IEEE, though, there are things like Collaboratech, which is a networking platform. There's life insurance, there's other discounts. If you want to go to an IEEE conference, the discount you get by being an IEEE member more than covers the cost of your membership. So it's worth joining that in some ways.
All right, well, that's all we have for questions. And unfortunately, due to time constraints, we're going to be skipping the break. Sorry about that. If you don't want to get up and stretch and stuff, I mean, feel free. But I'm going to introduce Fidel. We're going to Fidel this time to not be acting, so we're going to get a lot of applause. He really deserves it.
Howdy.
And you can stand up using stretch. I know so much of might go back to the back. Just stand, let's stretch. Make sure you don't touch your knee, but just go like this. Yeah, I'm not a sports science major, but I know one thing or two about it, so yes, just stretch a bit. Wow, so we are very interesting. We have three more sections coming up, very interesting. So because of time, we're not going to do the break, so I'm just going to go right into a very interesting session by Dr. Alisa and Dr. Michael. They're going to talk about, they're all the way from TIE, which is based in Austin. Please, can we welcome them to see?
Thank you for what you laid up here. My colleague, Professor Professor I'm also Director of our Semiconductor Science and Engineering program. This is
Alyssa Reinhardt, I'm the Director for Workforce Development for TIE, and excited to talk to you about our next generation microelectronics manufacturing program, or MGMM for short, and some of the opportunities for students.
Yeah, so I think I just wanted to start by kind of giving you a little bit of background on some of the reasons that MGMM exists, and why it's actually effective, how we actually committed to it, and so you've probably seen things like this before, where over the last 20 years, large scale is kind of ended. We're not getting faster kits anymore. Over the last 10 years, Moore's law has kind of ended, so we're not really producing more transistors as fast as we were before. And so there's a big push now towards going to advanced packaging as kind of a solution kind of team scale. So you can see kind of by 2030, some of the highest end devices are expected to have over 300 billion transistors on them. There's really no way to fit that kind of in a standard reticle size. Already some of those chips are getting gigantic, the yield getting terrible. And so there's a lot of kind of motivation towards going towards advanced packaging solutions to scaling of our production scaling and kind of put more into these sort of systems. And so what we see kind of over the last 15 years or so, this is really transition from basically humans being the primary users of data coming out of these electronic systems to industrial uses. Basically, machines are taking all the data, all the so yeah, you can see kind of this exponential trend in the amount of data that's being used by electronic systems, really driven by machines, robots, by AI hardware. And so it's really kind of transition from people to machines as are. And that means that there's been basically an exponential explosion in the amount of data that's being generated and being used in our microsystems. And so what that's meant is over basically the first 70 years of the lifetime of semiconductor design and manufacturing, it took about 70 years to do the first $1 trillion worth of business. So by 2012 or so, semiconductor industry was a $500 billion business. Now $1 trillion business. So over the last 7 years or so, that basically doubled in size. And the next $1 trillion will be probably another 3 years or so. And so this kind of scaling kind of the size of it is really driven by this increased use of data by machines, particularly kind of in this AI era, the amount of power and computation goes into some of those sorts of models and types of things that we're talking about. And so, like I said, the problem with that is our chips aren't getting necessarily better at the same rate they were in the past, and the demand for data and for processing power has gone up at an exponential rate. So we're not keeping up with, on a single chip, kind of the processing power we need to do. And so what that means is we need to figure out new ways to make our systems more efficient. And so just kind of building a better chip isn't doing it. We need to think about kind of the entire package, the entire system that we're working on. And so you kind of see this trend over the last 20 years, going from things like 3D system on package to kind of idea of package stacking and producing multiple packages stacked on top of each other, trying to increase our density of computational power to really getting rid of the package and stacking chips directly on top of each other. So 3D stacked ICs. Basically, we're stacking different silicon chips on top of each other in order to increase kind of the number of transistors, the compute power, the rate at which chips can talk to each other into a smaller form factor. And then kind of, as this continues to scale, kind of the next things that are happening are really building systems on chips. So basically, right now we have logic and memory as separate chips until we start to build those together on a single IC. What sorts of processes do we need to really do? Because those are very different sorts of manufacturing techniques to make those different types of chips. Very different sort of materials, very different, typically, pattern fidelities and pattern resolutions that are needed. You see this, at least in academic research, an idea of going towards basically transistor stacks, so layer transfer processes. So really going to sub-micron layer transfers on top of each other, getting integrated materials of different types in order to build up really high density of the types of packages you can build. And so you start to see that already. So if you look at some of the GPU modules out there, a common kind of thing you'll see is your computational chips combined with things like hyper-circuit memory, all combined into a single package, so you can get basically better data transmission rates between the memory and the logic. This is kind of a big problem in these kind of AI sort of applications. You have huge amounts of memory, huge amounts of storage that need to happen. You have huge data, and so transmitting that data between where you're doing processing and where you're storing it needs to be as efficient as possible. And bringing those things as close together as possible is really a key for doing that. And so you start to see kind of all these different now ways of combining chips to get more efficient for the system. So there's three kind of techniques that people develop. The idea here is kind of going towards this kind of what we call chiplet sort of economy, where I can have a different supplier of my memory, a different supplier of my logic, a different supplier of kind of other IP chiplets that might be in that system, kind of combine them all into a single package that works kind of like a single chip would work like in the past. So we're getting down to scalings of these interconnects that are on the order of sub-micron. And so we're getting to the point where basically the connections between different chips are at a similar resolution to what we would have done on a chip in the past. So that's really allowing us to kind of do these interesting sorts of scalings where we can start to stack multiple layers of memory on top of each other, have good kind of connections between those different layers, for things like high bandwidth memory, which has really been the key enabler for a lot of the AI technologies you see today. Or combining logic onto chips with that, and so you do this kind of 2.5D scaling, also kind of 3D scaling for things like flash memory. And so you're getting to kind of these really interesting sort of packages over the lifetime of our system. So yeah, over the last 20 years or so, what you've seen is kind of going from these kind of 2D layouts where you have chips like on a circuit board, all connected together, to these 2.5D layouts where I have an interposer, which has basically finer pitch interconnects, but still kind of works as a board that I'm sticking all my chips on. So now kind of our 3D stacking where I have interconnects going not only laterally on circuits, but down through chips into other chips, so we can have connections on multiple layers of chips. That way you see kind of a high bandwidth memory sort of application. And eventually going towards not only using silicon in these, but some other materials are great for other sorts of applications. I want to do high power computation, high power transmission. I want a different sort of material than silicon. If I want to include sensors and sensor arrays, MEMS devices onto a single specific stack of chips, that allows us to kind of 3D energy integration really allows us to get that sort of performance. And so particularly DARPA has been very interested in this. DARPA gets a lot of really complicated sensors where they want to have a measurement and then computation right there, not have to transmit that data somewhere else to get my processing of it. And so for the last 15 years or so, DARPA sponsored a few different programs, the DARPA CHIPS program, the DARPA Elder program, really kind of set the basis for 2.5D and 3D integrated systems. And so the problem that DARPA starts to run into is there's nowhere in the US to make these sorts of systems. So if you look at kind of semiconductor industry, still about 85% of design work is done in the United States. About 12% of front-end manufacturing is done in the US. Only about 3% packaging is done in the US. So packaging is not a place that I can go in the US kind of for my defense applications, find a foundry that's going to be able to make what I want to make, particularly as you get to these fine pitches and fine scales of packages. And so the DARPA engineering program is really focused on how do we create infrastructure for doing these sorts of packaging applications. So we create a US source for this. We create facilities that companies and research can go in and prototype new package designs with these kind of higher resolutions. Then we develop new techniques that allow us to do these things. We integrate a sensor with an RF device, with a memory, with a logic device, and do kind of all my computation at the edge where I'm trying to do my processing and do my measurement. And so that's kind of the idea behind the engineering program. So I'll let Alyssa kind of talk about TIE's approach to kind of dealing with that.
So a little bit of background on TIE, or Texas Institute for Electronics. We were founded in 2021, really in response to, we're seeing this need for advanced packaging and setting up the infrastructure and the ecosystem to be able to move us to be able to manufacture advanced packaging, or bring advanced packaging manufacturing especially here in the States. So the effort grew out of the previous NSF Engineering Research Center at UT Austin called NASENT. And we started, we had the Federal CHIPS Act. We then had the Texas CHIPS Act, which Texas A&M and UT were the two institutions within the state to receive funds from the Texas legislature through the Texas CHIPS Act to really position us to lead in the semiconductor industry. So with that, we were able to gain funding from the state to really renovate and bring up TIE and our facilities. And so we have two facilities in Austin. It's combined, we have 84,000 square feet of clean room space. And so this was, a part of this program is to bring up this to state-of-the-art equipment, to renovate and get them ready to be able to meet the needs for the DARPA program. So, like I mentioned, these are between our Montopolis and our Pickle campus. These are our flagship sites for the NGMF program, as well as beyond that for TIE. So these are, again, about 15 minutes apart. We have green space as well around them for future development if we want to. But we have, like I said, 84,000 square feet between the two sites. And I'll get to what the difference is between these two sites and how they go together in the ecosystem in a second. But so what I wanted to bring up, so who our partners are. You can see kind of our strategic partners, those that help sort of guide how TIE was created and our strategic plan and our vision, but also our industry and academic partners, which Texas A&M is one of our core partners for the NGMM project. And we also have additional within the industry, but we are, so TIE is a UT Austin sponsor and supported, initiative, but we're really a semiconductor consortium. So it's the intersection between academia, industry, and local government businesses. We're also working with national labs, so it's kind of separate in a way. So with the DARPA NGMM program, the core goals around this are one, developing this technology roadmap for this multi-material 3D HI manufacturing. So how do we actually bring this back and set up the infrastructure and the process for this? Two is this pilot manufacturing lab. So, and I'll talk about the pilot and prototyping facility in a second. Setting up, technology transfer pathways. So again, how you're getting, this is kind of, that valley depth. How do you bring technology out of the lab into the lab? And so that's a core part of our program. And then a comprehensive workforce development. I'll talk a little about that in a second. So, what you typically see, so where we kind of are a little bit different here, when you think about versatility versus manufacturing volume, you have at one end, you've got your typical university fab network where you can, there's a lot of freedom, and there's a lot of, it's a much more broad focus on what you can do, but you're doing very, very, very low yield. So there, that's at one end. The other end, your production jobs, this is Samsung down at the right bottom corner. So like when you're actually getting into large scale volume manufacturing. Where time comes in is again to kind of translate between the two. So our R&D fab, which is at our pickle site, is where you're starting to kind of develop, because you're doing a little bit more concentrated, more focused, still not high volume. But then once you get down to the prototype and pilot facility down on top of it, it's basically, we're kind of building a cookbook that's going to go out to the OSATs. So this is where it's much, you're getting closer to that high volume, but it's not quite the scale, or you're moving towards automation and everything that's and stuff. But a part of this, lack of standard processes, modeling tools and design. So that's really sort of working out that how do you get something again from the lab to the fab. So I'm not going to read all this to y'all, but these are the core components for our technology roadmap. I really think, how are we, what are the goals in addressing around manufacturing and microsystems? So related to this, and again, so TIE is both, we're part of ET, but we are an employer. We are, through the DARPA program, we have funding and opportunities. So we have a couple, including one Aggie, that will be starting with us this summer for our first undergraduate research experiences. We intend to have additional research experiences and internships in TIE. We also have a master's program, which I'll let Michael talk about, that is debuting this fall, where TIE is sponsoring several positions, fully funded for the master's. And also, as an employer, we're going to be employing up to 200, 250 engineers, technicians, computer scientists, and others to help run these facilities. So we also think of us as a potential future employer.
Yeah, so I guess, let me talk a little about some of the educational programs at TIE. So we have kind of three major initiatives that we have launched in the last few years. One is an undergraduate minor in semiconductors, which is a 5-course minor. You take kind of the intro semiconductor class, and you take 4 classes of specialization. Specializations include semiconductor manufacturing, circuits and systems, heterogeneous integration, and semiconductor devices are the 4 tracks that you can participate in. And so we have about 20 undergrads who are enrolled for this first year into that minor program. We expect that to expand significantly over the next couple of years. We also have a graduate certificate program. So it's a 3-course certificate program that's mostly intended for people who are working full-time to kind of transition into the semiconductor industry. Those 3 courses are part of also our master's program. And so if you take kind of the certificate program, translate those classes directly into our master's. And so there's 3 kind of core courses that are part of our master's program. There's an intro to semiconductors course, there's a semiconductor processes course, and a semiconductor devices course. And so the background for this is we want to expand beyond just kind of electrical engineers as the background for people who can enter these programs. Electrical engineers are great, but they don't necessarily fill out all the potential jobs in the semiconductor industry. And so we're looking at kind of the shortages that are happening in semiconductor employment right now. We need to really expand a broader pool of students. And so we take electrical engineers into this program, but we also take students from other disciplines as well. And so that kind of builds into our master's program. Our master's program, like I said, involves these kind of 3 core courses. We also have 2 lab courses which students participate in. Is the processing lab we're building out kind of a facility at our campus, as well as a ecology lab. For kind of going through full kind of design, build, fabrication, test cycle for our semiconductor manufacturing, as well as students also take a few classes specific to the track they're in. But the big part of this program is kind of the industry-sponsored research part of this department. So all our students participating in our master program are sponsored by an industry affiliate, working on an industry-sponsored project for multiple semesters during their program. It's a 3-semester program typically. Over the summer, usually they'll go and do an internship at the company that's sponsoring their research. And so what that means is the master program is a funded program. So students are receiving a stipend during their receiving tuition, and so it's very similar, kind of like a graduate assistantship program if you were like in a PhD program. And so basically we're paying students to come do master's degrees, sponsored by industry, and working on industry-related projects as part of that program. So for our first year that we launched, we have about 20 fellowships we gave out. I expect that number to grow over the next few years as more and more industry partners join our program. But it's really a chance to spend a couple semesters, work on an industry-related project, get the background you need to work in a semiconductor field, and really kind of move your career into that field as a transition for students coming out of undergrad or kind of transition from another. And so I think that gives us a little bit of background on kind of some of the educational programs that we're doing.
So, as I mentioned, so TIE is one of those industry sponsors for these projects. So, our focus would be on 3DHI, but there are relevant, not just within that, but it could be into with digital twins. It could be with circuit and design. There's a broad range. It's not just that one track that TIE is interested in. But are there industry sponsors at the moment are Samsung and Emerson, who are also interested in hiring and sponsoring students to do so, which would include the integration track. So I think we're pretty much at time, but is there time for questions? Or?
Yeah, hello. Yes, can we give them a round of applause, please? I think we have time for one question right now. Does anyone have a question?
So, great presentation. My question is regarding package level manufacturing. What do you guys think it would take to bring some of that to the US?
Yeah, I think we already see some of that coming to the US. Samsung has announced some memory packaging will be here. TSMC has a package for Intel has a package for so you already see some of that here. I don't think you'll see kind of wire bonding coming back to the US. There's just not enough value for cost in that. But something more advanced packaging where really you're getting processing that's very close to what the front-end processing kind of looks like, where the value is in the actual manufacturing process, in that packaging is adding significant value to the product, and it gives you a product differentiator between you and your competitors. That, I think, has the potential to come to the US. First of all, because it hasn't already been lost somewhere else since it's new. It's really hard to bring back stuff that's already been lost to a lower cost producer, but also because it really impacts the value of your product. I think what you see is with the history of semiconductor, the parts that aren't adding new value to the supply chain are things that are getting shipped off. So that's why design has stayed pretty sticky here. A lot of the value in the semiconductor is the design IP right now, and as the kind of manufacturing got more commoditized and got shipped offshore. But the advanced packaging really is a differentiator for these companies as they're standing up new products. And so I think that makes it a lot more palatable to bring back here.
And also, part of the goals with TIE is to basically be an accelerator to be able to enable more of that advanced work to be done domestically by doing this sort of cutting-edge research and translating it into production for domestic companies.
Okay, thank you so much. Please let's appreciate it. Well, we're almost there. We're doing well. Well, so,